Hello viewers, welcome you all. In this lecture, I am going to start the topic nuclear physics, right? Nuclear physics. In the earlier lectures, I have taken up the topics related to high energy physics or particle physics, right? We know very well that this is that uh, nuclear and particle physics is a very important part in any competitive exams, whether it is of UG level or PG level. 3 to 5 questions, as I told you, are asked from the particle physics, and the same number of questions, 3 to 5, are asked from the nuclear physics, right? So in total, if you have a command over this course, nuclear and particle physics, then around 10 questions you can do quite easily, right? But for that, you have to first of all have to have the good theoretical understanding of all the concepts of nuclear and particle physics, right? So in today's lecture, particularly, I am going to discuss with some general properties of atomic nucleus. General properties of atomic nucleus. I will cover up all the topics that are related to the general properties of atomic nucleus, and then after in the next lecture I will take up some questions, right, related to this topic, right? So now I'm coming to the main point. When we talk about the atomic nucleus, right, the discussion of the nucleus starts with the discovery of a nucleus through alpha ray scattering experiment by Ernest Rutherford, right? Rutherford alpha ray scattering experiment, right? And that experiment reveals that the whole positive charge of the nucleus is concentrated in a very small region at the center of the nucleus, right? And the 99.99% space in atom is empty, right? Only very small space is occupied by the matter, and the most of the mass is located at the center. And this experiment led to the discovery of this atomic nucleus. And then after, we have different theories about the composition of nucleus. The first theory was electron proton theory. I have explained all these in my course nuclear and particle physics. So the video lectures are available there. If you want to go in details, you can go to that course and watch all those videos, get the clarity what is electron proton theory. So electron proton theory, I'm taking up only the important points. Electron proton theory assumes that the nucleus contains protons plus electrons, right? But this theory has several objections, right? We know very well. The main objections against this theory was the first one was Bain mechanical consideration. I mean, calculating the energy of the electrons when they are present inside the nucleus. So the energy comes out to be of the order of 10 mega electron volt when we calculated this energy, right, by taking into consideration Heisenberg uncertainty principle and the momentum energy relation. But in reality, when the electron come out of nucleus through beta decay, then it is found that their energy is of the order of 3 to 4 mega electron volt. So this is the first objection, because these two quantities are not matching. It is quite larger than this one. So it means electron cannot exist inside the nucleus. This is the first objection. The second objection was a nuclear spin, right? So we should also remember that this is also against this electron proton theory, right? And according to electron proton theory, what was the model? The model was the nucleus contains Z protons, right? And it contains Z A minus Z electrons, right? And Z extra electrons also revolve around the nucleus. This was the model. Nucleus contains Z protons plus A minus Z electrons, and Z extra electrons also revolve around the nucleus. So this was the model. But according to this model, whatever spin we calculate, so that was not matching with the experimental measured spin. So nuclear spin concept was also against this theory. Then if I come to the nuclear magnetic dipole moment, right, then mu n. So it is also against this theory, right? Because the calculated value of the magnetic dipole moment of the nucleus, right, it was not matching with the theoretical predictions of this electron proton theory. This was also an objection, right? Then wavelength, right? If we calculate the wavelength of the electron inside the nucleus, right, then it comes to be very, very large than the size of the nucleus. We know the size of the nucleus is of the order of 10 raised to power minus 15 meter. But when we calculated this wavelength of the electron, when it is present inside the nucleus, lambda is equal to h upon p, right, according to de Broglie hypothesis, it comes to be very, very large than the size of the nucleus. It means how electron can present inside the nucleus. So all these are the objections which are against electron proton theory. So due to these objections, this theory was dropped and we have a proton neutron theory, right? And according to proton neutron theory, right, what was the composition of nucleus? Z protons plus A minus Z neutrons, right, and Z electrons are revolving around the nucleus. So this is the model, right, of a proton neutron theory, right. This theory came into existence with the discovery of neutrons, right. So this is proton neutron theory, right. Now I am coming to some other properties that are determined either experimentally or calculated theoretically about the atomic nucleus. The first one is right, the radius of the or size of the atomic nucleus. So it is found that the radius of the nucleus is directly proportional to a power 1 by 3. So we have to remember this relation. I can write R is equal to R naught a power 1 by 3, right. Here R naught is constant whose value is 1.2 to 1.4 Fermi, right. So this is about the size of atomic nucleus, right. Then if I come to the volume, right, volume obviously it is 4 by 3 pi r cube, right. So volume directly proportional to A. Why? Because R is equal to this A power 1 by 3 and volume, when we are taking that the nucleus is spherically symmetric, so it is equal to 4 by 3 pi r cube. So r cube means this cube, right. So obviously B directly proportional to A. So this is also important relation that we have to remember. Now I come to the nuclear density, right. Nuclear density. We know, I will call it as a nuclear mass density. We know very well that the density of the nucleus is of the order of 10 raised to power 17 kilogram per meter cube, right. So how we have calculated it? We calculated it simply by mass, total mass over total volume, right. So 10 raised to power 17 kilogram per meter cube approximately. Now the examiner can ask a question that you calculate the number of nucleons. Nucleons means either neutrons or proton per unit volume. How many number of nucleons are present in per unit volume? So how we can calculate this? We can calculate it by simply taking the density divided by the mass of one nucleon. When you calculate it, it comes out to be around 10 raised to power 44 nucleon per meter cube. This is a very, very important result that can be asked in the examination. What is this? Number of nucleon, number of neutron or proton per meter cube, right? And this is the density. So this relation comes from this one, right? So it can be asked, right? Now I am coming to some units that are used in nuclear and particle physics. One is the unit of mass, We have to remember all these relations and values. So unit of mass in nuclear and particle physics is AMU, atomic mass unit, right? We know very well what is it, and its value is 1.66 in 0 into 10 raised to power minus 27 kilogram. This is the atomic mass unit, and this unit is used in measuring the mass of subatomic particles. I mean neutron, proton, right, or electron, right? So if I write down the mass of neutron, right, mass of neutron, we know very well that the mass of neutron is higher than the mass of proton. But how much higher? This is very important. So if I write down the mass of neutron, then it comes up to be 1.00866 AMU. And what is mass of proton? 1.0072, right? Then 7 AMU. So this is the difference. You can see the difference. Difference is only in these three figures, right? But the mass of neutron is higher than the mass of proton. If I write the mass of electron in terms of AMU, it comes out to be 0.000549. So this is the mass of electron AMU. So we have to remember all these relations. Now, if I write the mass of these three particles, electron, proton, and neutron, in terms of energy, we know E is equal to mc square. So m is equal to E upon c square, right? So I can calculate the energy corresponding to this mass, right? Then I can write down the mass in terms of energy. So when we calculate it, it comes out to be mass of proton in terms of energy. It is around 938 mega electron volt, right, upon c square. So you can take the c as 1, right? Similarly, mass of neutron 939.5, right? It is 938 point exactly 27, right? And it is 939.57 mega electron volt. Similarly, the mass of electron 0.51 mega electron volt. So you can see the mass of the electron is very, very small as compared to mass of proton and mass of neutron, right? So we have to remember all these relations. Question can be asked from these relations, right? Now I am coming to the next property of atomic nucleus. The property is spin. Spin of a nucleus. We know the spin of nucleus will be obviously equal to the spin of protons plus spin of neutrons, and it will be I is equal to L plus S. Here L is the total orbital angular momentum, S is the total spin angular momentum of the individual particles. So when we will take the total angular momentum, so total angular momentum of the nucleus is called its spin. But it doesn't mean that it is only spin angular momentum. It contains both contributions, right? And we know very well that when we have discussed it in nuclear and particle physics, this topic, we have arrived at a conclusion that the spin I for a even nuclei is equal to 0. For a odd nuclei, it is integral, and for a even odd or odd even, it is a half integral, h cut, right? Integral multiple of h cut, right? So even odd means, what does it means? Even odd means z even, n even, z odd, n odd. Say z here number of protons, n here number of neutrons. So we have to remember this relation also, these results also, that the spin of even nucleus is equal to 0, odd nucleus is equal to integral multiple of h cut, even odd even is equal to half integral, right? So this is the concept of nuclear spin, right? We have to remember all these relations. Now I am coming to the magnetic dipole moment, right? Next property of atomic nucleus, magnetic dipole moment, right? So when we calculate the magnetic dipole moment, of the nucleus, then we have to calculate the magnetic dipole moment of a neutron, magnetic dipole moment of a proton. So when we calculated these magnetic dipole moments, it is found that the magnetic dipole moment of neutron is equal to minus 1 point, right, 9135 mu n. I'm going to discuss mu n, and this is 2.7927 mu n. Now here one thing that I want to make clear, that this magnetic dipole moment of the neutron and proton, it is only because of their spin, right? Spin angular momentum. The contribution of the orbital angular momentum is not here. It is their spin magnetic dipole moment, I can say. Spin magnetic dipole moment. Magnetic dipole moment of these elementary particles because of their quantum spin, right? And you can see here that neutron's magnetic dipole moment is a negative. It is usually asked in the examination, right? Because if we look at the neutron, it is a neutral particle. So, it should not have magnetic dipole moment. How a neutral particle can have, magnetic field associated with it? But it actually has, right? And similarly, proton is positively charged, so it can have magnetic dipole moment, can have magnetic field associated with it, because it is a charged particle. But the thing was that neutron has magnetic dipole moment and it is a negative, right? Now what is mu n? Mu n stands for a nuclear Bohr magneton, right? And it is a unit for the measurement of dipole moments of the nucleons, right? It is natural unit that is invented to measure the dipole moments of a nucleon. Nucleons means either neutron, proton, or other elementary particles. And mu n is equal to E h cut upon 2mp. We have to remember it, right? Again, it is a very, very important result. Magnetic dipole moment. Here also I talk about this, in the beginning, that what were the objections, right? So magnetic dipole moment was also an objection, right, for the proton electron theory, right? So why it was an objection? Because if we look at here, if the electron was present inside the nucleus, then the magnetic moment of the nucleus should be of the order of E h cut upon 2me, right? E means mass of electron. Now we know very well that the mass of electron is around 2000 times smaller than the mass of proton and a neutron. It means it will be, obviously, if I compare this with E h cut upon 2mp, right? So you can see here that I was saying that if I compare it with this, right, then this term is quite higher than this one, because mass of proton is high as compared to the mass of electron. So obviously this term will be around 2000 times than this term. But when experimentally the magnetic dipole moments of the nucleus were measured, then it was found that it is of the order of this value. It means electron cannot exist inside the nucleus. Otherwise, this factor should dominate inside the nucleus, right? So this was the reason. I again, recalled it. Now I was saying that this is the unit for the measurement of magnetic dipole moment inside the nucleus, and this is the unit for, we call it as electronic Bohr magneton, right? This term, right? And its value is around 9.27 into 10 raised to power minus 24 ampere meter square, right? But this is electronic Bohr magneton. Now examiner can ask you, right, about the values. What is the value of electronic Bohr magneton, or what is the value of a nuclear Bohr magneton? Now nuclear Bohr magneton, I'm writing it here, E h cut upon 2mp. So if I calculate the value of nuclear Bohr magneton, it will be 5.044 into 10 raised to power minus 27 joule per Tesla, or it can be converted into other units, 148 into 10 raised to power minus 8 electron volt per Tesla. So you can see here the energy is in the form of joule, it is in electron volt per Tesla, right? Now here I have taken the unit ampere meter square, but here they are in joules Tesla. So if you compare the dimensions, right, the dimensions are the same. Both the things, this one and this one, they have same dimension. They are magnetic dipole moments, right? So so don't worry about it. Don't bother about it. But we have to remember these values, right? That what is the value of a nuclear Bohr magneton and what is the value of a electronic Bohr magneton, right? It has two values in two different unit systems, and it is in ampere meter square that are commonly asked or discussed in the books, right? Now this was about the magnetic dipole moment. Now I am coming to the electric quadrupole moment. Electric quadrupole moment. So I have already discussed about the quadrupole moment in lecture. So you can refer to that lecture. So but we have found that the nucleus contain neutron and protons, and it is not spherically symmetric. It was found that most of the nuclei in the nature, they are not having perfect spherically symmetric shape, but they deviate from this spherically symmetric charge distribution. And it was found that the quadrupole moment of the nucleus, the value is given as it has two formulas for calculating it. One is it is 2 by 5 z e into b square minus a square, right? When we are talking about the general case of the nucleus, right? And when I talk about the nucleus that contain only single positive charge proton, then it comes out to be 1 by 2 or e by 2, simply e by 2 into 3 z square minus r square. So we have to remember these two formulas for the quadrupole moment, right? 2 by 5 z e b square minus a square for general case of nucleus that contain z number of proton, and it is for single proton, right? We know very well, if q is positive, right, the shape is a prolate, spheroid, right? And if q is negative, it is a oblate, spheroid. And if q is 0, then it is a perfectly sphere. These are the three different cases of the shapes of atomic nucleus according to the value of quadrupole moment of atomic nucleus, right? Now I am coming to the next property, that is mass defect and winding energy. So if I come across these topics, mass defect and winding energy, we know very well that mass defect is simply defined as the difference between the mass z time mass of proton plus a minus z mass of neutron. This whole term is always greater than the mass of the nucleus so formed. So this difference is called mass defect, and the energy corresponding to this mass defect is called winding energy of the nucleus. And when we divide this winding energy by A, we call that as average winding energy of the nucleus, right? Or we can say binding energy per nucleon. Now we have drawn a curve. I have discussed it in a separate lecture. In that I have drawn a graph between the binding energy per nucleon and mass number, and the graph was of this type, if I recall it, right? A, and this is a binding energy per nucleon. You can refer to that lecture. So usually question is asked from here that what is the average value of winding energy, right? So average value of winding energy is around 8 mega electron volt. What is the maximum value of winding energy? It is 8.8 mega electron volt, and it is for iron 56, right? So we have to remember it, right? And what is the value of the winding energy per nucleon for lighter nuclei? It is very low or small value. Again, for the very heavy nuclei, it is small, right? And in the intermediate range, it is a nearly constant, equal to 8 mega electron volt, and the maximum value is 8.8 mega electron volts. So all these things has been taken up, right? And the one thing that I forgot to tell you, that in the region of small mass numbers, you can see we have sharply defined peaks, right? These peaks corresponds to maxima, and these are corresponds to 2He4, right? Then beryllium 8, right? 10, right? Similarly, 6 carbon 12, right? These are the peaks. 8 oxygen 16. These are the peaks that corresponds to the higher value of winding energy per nucleon, and they corresponds to these nuclei, right? So examiner can ask questions from here, that these peaks corresponds to which nuclei, or which nuclei has very high winding energy as compared to its nearest neighbor, right? So this is about the binding energy and mass defect. Even a question can be asked from the binding energy. You can be asked. You will be given a reaction, and you will be given the values of the mass of proton, mass of neutron, right, and the mass of the given nucleus, and you will be asked to calculate the binding energy. So you can simply calculate the binding energy, right, by using this relation, delta E is equal to delta m c square, right? Now I am coming to the next, that is packing fraction. Now again, packing fraction we know very well, it is linked with the deviation of atomic mass from whole numbers, right? I have explained it in detail, atomic mass from whole numbers, and it is defined as a packing fraction is equal to atomic mass minus mass number divided by mass number, right? It is written as a F. If we look at the graph of packing fraction, then it comes out to be right. If I draw the graph, roughly I am drawing it. So we know very well that it comes out to be of this, right? This is the value of the packing fraction. This is mass number, right? It is around 16, and it is around 200, right? And the intermediate nuclei in this range, they have negative value of the packing fraction, and they are highly stable. But if we go toward this side, the packing fraction is positive, unstable, packing fraction positive, unstable. So we have to again remember this graph. And what is packing fraction? You can be asked to calculate the value of the packing fraction. But remember, once again, I make you aware that packing fraction is somewhere written as a mass defect per unit nucleon. But this is wrong, right? I have also explained this in that lecture where I have discussed about the packing fraction. So packing fraction basically means atomic mass minus mass number, right? It is the deviation of the atomic mass from a whole number, right? Now I am coming to the next topic, and it is nuclear stability, right? Stability graph. So I have also discussed this in different lecture. You can refer to that. And what was the observations? I'm drawing it with the help of it. Right. So it was observed when we discussed and studied the stability of different nuclei that exist in nature. Then it was found that for the lighter nuclei, right, Z is equal to N. or n is equal to z. But as we move forward, right, go beyond this point, that is around 20, then it is found that the number of neutron start increasing and n becomes greater than z, and we get this type of region, right? This region is called stability zone, right? Stability zone. So most of the stable nuclei, they exist in this zone, right? And you can see that the graph is deviated toward the neutron side, right? Toward the neutron side, it means number of neutrons are higher than number of protons in those nuclei for which mass number is high, right? I mean heavy nuclei. So here examiner can ask a question. I have explained it also there, that if uh, a nucleus undergoes beta negative decay or beta positive decay or alpha decay, then how we can represent it on this graph? So it is found that if the nucleus undergo beta positive decay, then it will lie toward this side. If undergoes beta negative decay, it will be present here, right? If alpha decay, it will be present here. Beta decay means the nucleus, when it is present here, it want to come in this region, right? So it can come here by simply increasing its Z. So we know very well in beta negative decay, I mean electron emission, right? We have a neutron convert into proton plus electron plus anti-neutrino. So obviously number of protons increase, Z increase, right? So beta negative decay will be from this side, right? And the nucleus will come in this stability zone. Similarly, beta positive will from this side, and the nucleus will come in this stability zone. Alpha decay means we will have a decrease of 4 by mass number and 2 by number of protons, right? Alpha particle is basically a helium nucleus, 2He4, combination of 2 protons and 2 neutrons. So when a nucleus undergoes alpha decay, its mass number is decreased by 4 and atomic number is decreased by 2. But in beta negative decay, this reaction takes place in the nucleus, and in beta positive decay, proton convert to neutron plus positron plus anti-neutrino. This is the reaction that takes place inside the nucleus, right? This is beta negative and this is beta positive. So you can see. So this is very, very important graph, and usually question is asked from here, and the question will be of this type, that beta decay will take place, beta negative decay will take place from which side, positive decay will take place from which side, alpha decay will take place from which side, right? So this is about all these property. Now there are also some basic things related to the general properties of atomic nucleus that we should know. That is, what are isotopes? So no, we know very well what are isotopes. These are different types of nuclei. Then isobars. Isotopes means what? The nucleus that has same Z but different A, right? Isobar, same A but different Z, right? Then isotope, I can take examples. 1H, 1, 1H, 2, 1H3, right? These are different isotopes of hydrogen. But when I come to isobars, will have a same mass number but different, either atomic number or different number of neutrons. We can take up examples of different isobars like 50 in 131, right? And 51 antimony 131. So you can see here the mass number is same, but the number of protons is different, right? So these are some examples of isobar, right? Same mass number but different atomic number, right? Or it can be different number of neutrons, right? But the mass number will remain same, right? Obviously, when here we have 131 total mass number, protons are 50. So number of neutrons, I can calculate the number of neutrons here. 131 plus 50, right? So 81, right? 81 neutrons are there, right? And in this case, 131, 51, 0, 80 neutrons are. So neutrons are also different. So as I told you, isobar, same mass number, different Z and N. Then isotones. What are isotones? The nuclei will have same value of N. Isotones means same number of neutron, but can have a different value of A or Z, right? But the number of neutron is same. For example, 1H3 and 2He4. Now you can see here 2 neutrons and 2 neutrons in both the cases. Number of neutrons are same, right? You can have similarly other examples. So this is about the isotones. Now next one is mirror nuclei. So in mirror nuclei, the number of neutrons in one nucleus is equal to number of protons in other. This is the case of mirror nuclei. Number of neutrons in one nucleus is equal to number of proton in other nucleus, right? So we can have example here of mirror nuclei, that is 8 oxygen 15 and 7 nitrogen 15, right? So we can see 8 proton and here 8 neutron, right? 8 proton and 8 neutron. So what I said, the number of neutron in one nucleus is equal to number of proton in other. So these type of nuclei are called mirror nuclei, right? So these are the different categories of nuclei: mirror nuclei, isotones, right? Then isobars, isotopes, right? These are different cases. And then I have last one, that is isomers. Isomers are basically the long-lived excited states of some nuclei. Long-lived means those excited state that has lifetime greater than 10 raised to power minus 9 second. So these, the excited states of those nuclei are known as isomers, right? Now this is about all these things. Now I am coming to the properties of nuclear forces. So I have already explained the property of nuclear forces in the discussion of high energy physics. So I am not coming to it again, right? We have discussed that, but nuclear forces, what is the field particle in nuclear forces, right? How they act. I am coming to the Yukawa theory of nuclear forces. So we know very well that according to Yukawa theory of nuclear forces, right, there is continuous exchange of pi mesons, pi positive, pi naught, and pi negative particle among the nucleons. And because of this, the nucleons are held together inside the nucleus. So usually examiner can ask from here that which particle is involved in the interaction of a neutron-neutron. So we know very well that when there is a exchange of neutral particle, right, neutral pi meson, then we can write that neutrons gives pi naught plus neutron dash. Then neutron dash plus pi naught will give you again neutron. So neutral pi meson is involved in the interaction of a neutron-neutron and a proton-proton. Same way, proton gives a pi naught plus new proton dash, new state of proton, then proton dash plus pi naught, that will give you proton. So this neutral particle is involved in the interaction of a proton-proton or neutron-neutron, whereas pi positive and pi negative are involved in the interaction between the neutron and a proton with these relations, that protons give a neutron plus pi positive, then the another neutron will take this pi positive and it will change into proton. In the same way, neutron will uh, goes to proton plus pi negative. Similarly, proton plus pi negative, that will give you neutron. So these are the different reactions. As far as the mass of pi mesons concerned, it is 270 times mass of electron, right? They are boson particles, right, having spin equal to 0, right? So we have to remember all these properties of pi mesons. This is 270 times mass of electron. If I write it in terms of energy, it is of the order of 100 mega electron volt. We have to also remember it, right? 100 mega electron volt. That is mass of pi mesons, right? So this is Yukawa theory of nuclear forces, that we call exchange theory of nuclear forces, right? And according to this theory, then neutron and protons are held together inside the nucleus because of the exchange of pi mesons, right? So I have covered up all these basic properties of the atomic nucleus, right? And if you want to go in details in any of this property, then you can refer to my online course about the nuclear and particle physics. All these topics has been covered in those video lectures in detail. So I have taken only the important points from these topics, right? I have recalled all these things. One thing that I forget to tell you in case of Yukawa theory. So Yukawa potential, I mean potential that exists between the two nucleons is of the minus g square exponential of r upon r, right, divided by r, right? So this is the expression for Yukawa potential. Yukawa potential between two nucleons inside the nucleus. So we have to also remember it. And if I plot this Yukawa potential, then it found that it follow this type of relation, right? This is Yukawa potential. This is distance of nucleon, between them. Right? So you can see here. So this is all about all these things that I discussed in the lecture. Now in the coming lecture, next lecture, I will take up important questions from these topics that has been asked in different competitive exams, right? Once again I am saying that I have taken up only important points. If you want to go in details, you refer to the video lectures related to that topic, right? So thank you very much.